Now we are going to start our second paper session, and our first speaker, the presenter, is going to be Nitin Kohli. He is a scientist from UC Berkeley. Uh, he's going to talk about enabling responsible use of personal data with targeted differential privacy. So, Nitin, over to you, please.
Hi, thank you all. Let me share my screen. Hi, everyone. Thanks for the introduction. My name is Nitin. I'm a staff scientist and principal investigator of the Data Privacy Lab at UC Berkeley's Center for Effective Global Action. The Center for Effective Global Action is a research and innovation hub that aims to reduce and eliminate poverty. And I'm here to talk to you today about what we can do to enable humanitarian applications using privacy-enhancing technologies such as differential privacy, what I'm going to talk today about targeted differential privacy. And I want to just point out that the work I'm going to show today is collaboration with Professor Joshua Blumenstock. And this is a forthcoming paper, so the slides have preliminary results in there. So that being said, let's talk about privacy and humanitarian aid and how it connects to consumer finance a bit. To set the stage, I kind of want to take us back to the year 2020 to build some motivation. So in 2020, many governments around the world sought to provide economic relief to their citizens during the COVID-19 pandemic. For example, in the United States, the government passed the CARES Act, which sought to give individuals monetary transfers if their previous year's tax filing was below a certain threshold. So that program in the United States was a targeting approach where we identified individuals based off of their income levels for a cash transfer. But in low and middle income countries, which is the context I particularly work in, many governments actually don't have administrative records. So for example, the government of Togo, which is a West African country that you can see kind of this little sliver there of around 8 million people, didn't have administrative data on, the poverty levels of their citizens when the COVID-19 pandemic hit. But at the same time, the government wanted to provide economic relief to individuals experiencing hardships. So they launched what was called the Novisi program. It was probably the first ever, if not one of the first ever, digital emergency cash transfer programs that sought to provide the poorest individuals living in the poorest regions $13 to $15 per month for 5 months. But once again, Togo didn't have any administrative data, so they kind of faced an information asymmetry of how do they identify who's in need. And many of us kind of know that we can use non-traditional data sources to learn about people's wealth, their credit scores, and their poverty status. So in particular, in low and middle income countries, the way poor individuals use their phones is quite different than the way rich individuals use their phones. So for example, if we observe in mobile phone metadata, which is, data about data, that an individual is making a bunch of international phone calls consistently over a long period of time, they likely have a data plan that lets them do so, so it's unlikely that they're experiencing poverty. For example, another one could be if we notice through metadata that somebody is on social media like TikTok all day, then they likely have a data plan that lets them do so. They're unlikely to be below the poverty line. And we can see that there are other characteristics that we can observe in mobile phone metadata as well. So in these orange charts, plots, we have people who we know are for sure living in poverty. And in the blue, we have people who aren't. And we could see that depending on the number of times people recharge their phones in a day, there is a little bit of a difference between the distribution of how these two are. Similar for like the percent of times initiated interactions happen, versed off of the entropy from weekend day calls and so on and so forth. So while it's the case that these features alone don't perfectly bifurcate poverty versus non-poverty individuals, what we could do is use a machine learning model to kind of consider these features in aggregate with one another to try to predict who's experiencing poverty and not. And this approach actually has been used not just in Togo, but also in Afghanistan and Rwanda, where we actually see that there is a pretty decent R-squared from trying to predict somebody's wealth from mobile phone data when compared to their actual wealth. And the use of mobile phone metadata, or what I'm going to abbreviate as MPMD for the rest of this talk, because it's going to come up a lot, for targeting applications can be used not just for anti-poverty benefits like I've motivated here, but also for digital credit and instant loans, particularly in low and middle income countries where individuals might not have a formal financial history. However, in these settings, an individual might still be a low default risk, even though the bank might not have information about them. So there are certain countries that actually rely on mobile phone metadata through partnerships with telcos to be able to then create alternative credit scores to be able to identify low-risk borrowers. But as with every data set, there always is a risk of privacy concerns. And I actually just want us to stare at this mobile phone metadata screenshot here. And when we look at this, we might say, Nitin, what are you absolutely talking about here? How could there be any privacy risks there? There's some gibberish from a mobile phone to some other gibberish from a mobile phone. That was a phone call sometime in the year 2015. And sure, when we look at it like this, things are obfuscated. But the point is that data can reveal things beyond how it's explicitly encoded. So there are a few things about mobile phone metadata that make it particularly controversial and sensitive in even humanitarian use cases. So in the figure in the top right, we kind of see that there's like this chart that says the uniqueness of individuals and their number of data points we have on them. So at an intuitive level, this came out from, I believe, the European Union. If we know 2 random location points about an individual, we can identify roughly 50% of the population. And this kind of makes intuitive sense. How many people went from where you live to your place of work? Unless you happen to work with your roommate or your housemate, the answer is 1. And this only gets worse as we get more and more data points about an individual, such that if we have 4 random data points on somebody, that your location trace is unique to 95% of the population. So even though we have all this kind of gibberish that's encoded up here and hashed, we can still notice that many of these traces will be identifiable. But even more so, we know that locations actually can invoke social meanings. So when I know somebody's GPS location, I could then identify that to where they are. As in this example, this individual traveled to a Weight Watchers. Conversely, it's not just that locations can leak social information, but that or social information can leak stuff about an individual, but also the way patterns reappear over and over again can actually leak strategic information about military bases, for example. So this was a case back with Strava, where location information showed a bunch of individuals that were running around this particular region, and it actually revealed a secret military base. So one thing that's important here is that mobile phone metadata actually contains a lot of location information. And most of us throughout the day always have our phone on us, except for very rare times. So because we carry this phone with us and locations have social meaning, we actually run the risk of learning too much about individuals that's beyond the scope of a humanitarian task, such as giving out anti-poverty benefits or figuring out who's a good credit risk. So let's see if we can attenuate this in some ways. And what I want to do is kind of get present an abstraction of the process we're going to think about. So let's imagine we have a bunch of individuals who are mobile phone users and a telco collects data on them. Their original data that has no privacy guarantee is going to be called dataset X. And we want to somehow sanitize this using a privacy enhancing technology that I'll tell you more about in a little bit, to create a privatized dataset XPriv, such that when I combine it with target information, we can still use machine learning to have social welfare improving applications, such as digital loans and humanitarian aid. But the key here is that I want to make sure that when we use the privatized data, we don't learn too much about individuals in the original data set. We don't learn about the facts of life of them that are beyond what is necessary to do our job. And there are many different privacy enhancing technologies that exist. And today we're going to focus on those that introduce what we're going to call carefully crafted noise to meet a somewhat meaningful guarantee of privacy. So this is the flowchart we have in our mind. We have a mobile network operator that wants to share data with maybe a bank, a government, or researchers, so they can still perform machine learning on to do good stuff while minimizing the risk of bad stuff happening by learning too much about them. Sorry, before I go on though, one thing we'll notice is that as we add noise to data, privacy is not going to come for free. So in order to create the privacy, we're going to add a bit of noise. But as we add noise, we expect our machine learning predictions to be less accurate. So in the case of humanitarian aid, we might have false positives and false negatives with respect to aid allocation, and same with digital credit loans. So the main thing I'm interested in is what's the privacy program effectiveness trade-off when these privacy-enhancing technologies are deployed in humanitarian applications. That is, as I turn the knob of privacy higher, how many people who are experiencing poverty might not get aid anymore? Or how many people who are eligible for a loan might be misclassified now? And are there judicious ways that we can navigate this trade-off in practice? So what I want to do is actually go through two case studies here. The first is going to be revisiting this anti-poverty program that I told you about in the beginning, the Novisi program. And the second is actually going to be about trying to predict who is a low or high credit risk using data from a Nigerian lender. And what we have is we have X data, X variables, so features on mobile phone metadata usage. And we're going to predict, slightly different things in each one of these categories. So if we want to actually talk about privacy, I need to do a brief mathematical interlude on differential privacy. And I'm not sure if folks have ever seen this before, so I'm going to spend 5 minutes kind of just laying down the background so the rest of the talk is kind of nice. And if you're already world experts on differential privacy, that's cool. So differential privacy is one of the most popular privacy-enhancing technologies. In fact, in President Biden's executive order on October 30th, with respect to AI and whatnot, privacy-enhancing technologies were mentioned, and so was differential privacy. Differential privacy was created to create privacy-preserving statistics. So the goal of differential privacy is to let you learn about a population without learning too much about any individual. So if we imagine that we're like a public health department, for example, and we're releasing statistics on just health outcomes for the population, maybe for a city, we want to make sure that the statistics we release still let us learn about the general trends of health, but don't let us accidentally identify somebody who is experiencing a disease. And the way we do this is we're going to add very clever noise to mask the contribution that any individual would make to a statistic. So if all this seems kind of abstract, here's a pretty picture. Let's imagine two parallel worlds, one in which your data is in the public health database and your data is X, versus a different one where your data is X prime. So this could be you didn't get COVID in 2020, and this could be maybe you did get COVID in 2020. Differential privacy guarantees that if you pass these to a very clever randomized computation, we'll get the same answer with essentially the same probability. So what this means then is that any adversary who looks at the output won't be able to tell if your data in the data set was X or X prime because they occur with roughly the same probability. So we can actually kind of formalize this a little bit. This says for any databases that differ in one person, the probability of the same outcome is essentially the same. Where us mathematicians love our epsilon and deltas, we parameterize this to say they're essentially the same up to factors epsilon and delta for those who are curious. So differential privacy is cool because it allows us to learn about population level trends without learning too much about an individual, which makes it great for statistical tasks. So one might hope that we could use differential privacy out of the box in the targeting setting that we had in Novisi or in this digital credit platform. But we kind of run into a problem here in that if we use differential privacy compared to the baseline case where there was no privacy at all, so this was just creating models using the non-private data, we see that in the case for targeting in Togo, we actually lose around 5% in accuracy. And in Nigeria, our credit scoring model drops from roughly 80% accurate to down to basically 63-ish. And we might start to say, okay, what does 5% and 15% translate to? Well, in these cases, it means around 115,000 people who are experiencing poverty wouldn't get aid anymore if I use differential privacy. Or in the case of digital credit, 430% profit loss would be incurred by the digital credit platform. And just to sanity check this, I also used another privacy enhancing technology called k-anonymity, and it also suffered similar things. So it kind of pointed to the fact that commonly used pets have stark trade-offs. So if we kind of debug this a little bit, we kind of see that targeting requires us to learn about individuals. So there's a conceptual mismatch here with some existing pets and new applications that require us to identify individuals. So for the case of differential privacy, if I had these two data sets, X and X prime, that had all the rows the same except for the first one, we would have the same chance of getting a private data set that we would try to build a model off of. But this is kind of tricky though, because this means regardless if somebody's poor or somebody's rich, we get the same data set at the end. So there's absolutely very little chance of a machine learning model to really learn about poverty status then, or to learn about who's a high or low risk borrower. So what this means then is that we have to actually adapt existing tools, existing privacy enhancing technologies to learn well about individuals while still protecting some meaningful notion of privacy. So to do this, we kind of tweak the definition of differential privacy. We still want to enable population level learning because we need to learn about poverty in general or about creditworthiness in general. But we still have to learn enough about an individual to learn whether they are poor or not poor, but not much else beyond that. So a lot of the technical work I've been focusing on is actually ways to do this. And if folks are curious, they can ask me more questions during the Q&A. But the neat thing is when we actually make this algorithmic change to the privacy enhancing technology, we see that the accuracy loss in the Togo anti-poverty example is quite minuscule. It drops from like 68%, 68.3 just down to 68. And our credit scoring model is quite as more accurate as well, around just shy of a 1% loss in accuracy. So whereas before in anti-poverty, many folks wouldn't be able to get their benefits, we only lose out on 2,000 people now compared to 115,000, which is quite a big gap to close. Not perfect, but still quite a big gap to close. And similarly, whereas before a bank would have lost around 430% in profit from this program using existing pets, we get it down to 12. And once again, I want to say these are not like perfect still, but they're on the road to getting there for future advancements. Now, because I've changed the definition of privacy in order to have more accuracy, we might be worried that these new privacy measures don't stop existing threats. So one thing I did was we measured here that the accuracy improved quite a bit, but let's see how much privacy we lose now. And what I did is I actually attacked these privatized data sets myself using two very modern attacks that are actually mentioned in the GDPR. So for those of you who are curious, you can look up its Article 29, Working Party 216 of the GDPR. They mention that there are a few types of attacks that they're worried about. One is called a singling out attack, and the other is an attribute inference attack. So singling out attacks, imagine the following scenario. Suppose researchers or a bank get this privatized data set, but there's an adversarial researcher or an adversarial bank employee. Could that researcher or bank employee still be able to isolate an individual's row inside the non-private data, even after we sanitized it? So that's what a singling out attack is. It tries to isolate an individual's row in the data set we didn't get using the sanitized one we did. So kind of reverse engineering, or you need some analytical alchemy to find out like what my record could be in there, for example. The other threat is called an attribute inference attack. And these are actually kind of sneaky. So once again, we imagine like an adversarial banker or an adversarial researcher who maybe goes and buys a subset of the data set from a data broker. So whereas before they only had the sanitized information, they get a little bit extra information from a data broker, and their goal is to try to predict the remaining columns that they didn't have. So in this example here, they would use the sanitized data set plus the real values they got for column 2, 3, 4, and 7 to predict the unknown values. So in this case, attribute inference attacks try to rebuild the data set in a column-wise manner, whereas singling out attacks try to identify an individual's row in the original data set. And one thing we find is actually that targeted differential privacy gets you a good chunk of the way there in particular. So in this Togo example here, we have our privacy protection against singling out on the x-axis and the left side, and the additional exclusion errors from using a privacy-enhancing technology. In the bottom left corner, there's essentially no singling out protection, and there's no additional errors because this was the non-private data. And what we find is using these tools, we can actually start to ramp up privacy a bit to the point where we start to see that, hey, you're around like 83% protected at the exchange of only 2,000 individuals being misidentified. But if we go to differential privacy, which has near perfect protection, the accuracy loss becomes untenable because around 115,000 people don't get anti-poverty benefits anymore. So this is kind of neat that we can actually chart out the contours of the privacy accuracy trade-off and what it means for humanitarian aid. In the attribute inference column, it's a similar-ish story, but we actually see something slightly more subtle. Once again, there was essentially no protection without any privacy, and targeted differential privacy got us around 80% protection. But differential privacy didn't buy us much more in terms of protection. So we actually see in this case that there are some types of attacks that are better suited for some privacy definitions. And in all of these cases, though, we see that actually by just using this modified notion of targeted differential privacy, there's a much better accuracy loss and better program effectiveness with orders of magnitude higher privacy protection that already exists. In the digital lending platform, there's kind of a similar story. So once again, we're going to consider singling out protection on the x-axis, and we're going to consider the bank's change in profit on the y-axis, just from this lending program. We see that had we used differential privacy, there's like untenable amounts of profit loss that no bank would ever use this, right? But using targeted differential privacy, we get around 85% protection when we had almost none before. And it only comes at the cost of 12% loss in profit. And you can note that actually, if an organization is willing to tolerate higher risk, they could actually edge this closer to maybe 2 or 3% profit loss and hang out over here at a 70% privacy protection. So these tools are great because they allow us to give decision makers tangible and legible ways to understand trade-offs and help with their risk management strategy themselves for privacy. For attribute inference protection, though, something funny kind of happened in this Nigeria example. We actually saw that you increase privacy up to a point using our method, but after a certain point, you actually become easier to identify using existing pets. And we do have some theoretical justifications for this, but this kind of also shows that when we talk about protecting privacy, we always have to say privacy in what sense? Because if I measure privacy with singling out, I have a very different story than if I measure privacy with attribute inference. So there's not only just a privacy accuracy trade-off or a privacy program effectiveness trade-off, there might be a privacy trade-off depending on what we seek to protect in our systems. So what's the moral of the story here, right? In many low and middle income countries, we're using personal data for a whole range of humanitarian applications. And because we're using personal data, we may introduce privacy risk, even though we set out to do something that was socially enhancing. And existing pets, like differential privacy, for example, were created for statistical tasks, so we just can't unthinkingly use them in new domains and hope they work well. In these cases, we might have to actually use domain expertise to tweak the math a bit in order to make sure that we're attending to the goals we want. And when we actually do this, it's important to be good scientists and transparently measure the trade-offs we get when we introduce these new technologies. So that's what much of my work does, and that's what much of what I tried to show you today, is that when we use pets, the increased privacy comes at a cost. And as long as we can characterize this trade-off, we can help decision makers, make more judicious and actionable decisions with respect to their programs. And I'll stop sharing. I'll take questions.
Yes, Nitin, thank you. Let's go over some questions that are posted. So one question we have here is, how do you set the benchmark of what percent loss in accuracy versus the percent gain in privacy is an acceptable threshold? For example, subprime lender, a 5% change in accuracy can result in a huge runoffs.
Sure. So this is one thing where I want to state that when I did these in the context of the research, I had to be very careful because as we move from one domain to another, the implications of trade-offs are completely different. So that's one thing that I like to tell folks is I design tools to help make these trade-offs legible to decision makers. But I'm a scientist. I'm not the one making the decision here. This is folks who work in banks, who work in subprime lending, or who work in humanitarian aid, who understand the trade-offs for their program, and then they set based off of the goals they need. So for example, in some cases, if it's the case that you would never actually get the data from the mobile network provider unless you had a reasonable amount of privacy guarantee, then that's just the accuracy loss you're going to have to deal with. That's one example. But yeah, it turns out that it really just depends. And these are things that you all have to chat with your legal department, with your program managers. And as long as you have good scientific tools that make these trade-offs legible and actionable, this is a great way then to start conversations with folks on what trade-offs are acceptable and how we can actually eke out better performance. Oh, I think you're muted accidentally.
Yeah, I am. I was. Yeah. The next question is, are there different best practices for implementing targeted differential privacy in various industries? For example, healthcare, finance, social media, etc. How to ensure that the differential privacy techniques do not degrade utility of data?
Yeah, so I guess I'm going to answer this question in two parts. So there are actually certain, I want to say there's somewhere between norms and standards for differential privacy in the classic sense that I kind of motivated earlier as being created for classic statistics. I believe NIST has some guidance on this, as well as other researchers and organizations that put out how they navigate these trade-offs. And one thing we'll note is that tech companies, for example, navigate these trade-offs very differently than public health departments would, or like a census bureau would, where the risk of a privacy breach means different things. For example, in like the case of the US Census, if census records are reconstructed and re-identified, that then poses threats to people not filling out census forms and then not getting the benefits of the things that the census does, such as funding for foster care, funding for roads, et cetera. That's very different than like LinkedIn or a platform that's a tech company that wants to make sure advertisers don't learn about other advertisers. So the context really matters here. And targeted differential privacy has no best practices because I'm still writing the paper and it will be posted on the archive soon. But yes, there is some guidance for some pets that exist.
There are a few more questions, if you don't mind going over the chat and if you can address some of those. In the interest of time, we'll probably move on. Thank you so much, Nitin, for your presentation. We do have Nestor. Yeah. Wow. Hi, Nestor. Hi. So you're going to talk about ML/AI revolution and impact on consumer finance. Is that right?
Yeah, I think it's going to be a bit more of a high-level presentation that is going to look at some trends that we see in the AI space and kind of put you guys in a position to understand some of the things that are going on with this technology. And then I'll leave you guys some opportunities to also be posing and asking questions.
Sure.
So thank you very much for having me today. I'm super excited to be chatting. And as I kind of alluded to in the presentation today, I'm going to be talking about, on a very high level, what's going on with AI technology. Now, before I actually do that, I'm going to try to convince you guys as to why you should listen to what I have to say. Who am I? What am I speaking on behalf of? So, I'm the research manager of the AI Index. It's an annual report that is currently in its 7th edition, and it aims to track, distill, and visualize key informations on trends in AI from a variety of perspectives. And the report was put together by a diverse steering committee of really influential AI thought leaders, people like Jack Clark, who's one of the co-founders of Anthropic, one of OpenAI's biggest rivals, Eric Brynjolfsson, who leads the Stanford Digital Economy Lab, and I would say is the world's leading scholar on AI and the economy, and James Manika, who is the leader of AI research efforts at Google. These individuals came together because they really understood that AI was going to be a groundbreaking technology, and that as such, it was going to be necessary to come up with some kind of report that could really track in very quantifiable and really rigorous ways what exactly is happening with this technology. And that's really what we aim to do at the report. Last year's version was close to 500 pages. And in the report, we looked at what this technology can do, what it can't do. We looked at how businesses are thinking of integrating some of these particular tools. And we also looked at questions related to responsible AI use, questions related to research and development, which countries are leading the research of AI, and questions that also related to public opinion. So I like to say that if there's any particular questions that you might have about AI, I can bet you that you might find the answer in the AI Index report. Now, in order to publish the report, we collaborate with a variety of data vendors. In certain cases, we do collect some of the data ourselves if we feel that this kind of data is not widely available. But generally speaking, we have good relationships with different data vendors like GitHub, like McKinsey, like CAS, which have given us a lot of very good labor data. These are really important partners in ensuring that the integrity of the index's data is maintained. And over the years, we've been privileged enough to have been covered in newspapers across the globe and also to have been cited by governments across the globe. So I think we've really positioned ourselves as a thought leader when it comes to trying to give policymakers and business leaders a sense of what's happening with this technology. And this is a thought leadership role that we're very eager and excited about continuing. Now, as I kind of alluded to earlier, the report itself is 500 pages. And I have, 30 minutes, including questions. So I'm going to try to distill the report into 10 takeaways, but I think this will give you a good sense of where we are with the technology as a whole, and hopefully be useful as serving as kind of a foundation for some kind of subsequent discussions we could have about some of the developments occurring in the space. So first and foremost is the highlight that AI is just getting better. And I don't think that is surprising to anybody. You're probably thinking to yourself, we didn't need to get a guy in from Stanford to tell us that. But I think the specific contours and the specific ways in which this technology is improving is really interesting. So here, for example, you see mid-journey generations over time of a hyper-realistic image of Harry Potter. So Midjourney, for those of you unfamiliar, is arguably one of the world's leading text-to-image generators. And what we did for Midjourney is we asked it to give us an image of Harry Potter, one that's hyper-realistic. And we asked that question to the original version of Midjourney, as well as the most recent version that was released. Now, I think this slide really makes it quite clear how much better AI has gotten in the last 2 years. Now, I personally am more a fan of postmodernism. I like Pablo Picasso, and the Harry Potter rendering on the left looks to me like Pablo Picasso has met Harry Potter. But of course, we asked for this system to give us a hyper-realistic image, and it's really the image on the right that kind of conveys that a lot more faithfully. Now, in more technical terms, you can really say that it's the case that AI now kind of beats humans on a lot of tasks, not all, but a lot of them. What you see on this particular slide is you see the performance of AI on a variety of benchmarks relative to human performance. So for those in the audience that are unfamiliar, benchmarks are kind of ways of gauging how well AI systems can do certain things. And usually they kind of consist of problems or challenges that AI systems can be tested on. Now, I think there's two key takeaways when it comes to this chart. The first is that we're now kind of seeing a much more rapid improvement of performance and improvement of speed. Now, you'll notice that the benchmark on the far left, the one that's in the blue, that's the benchmark for ImageNet. This is one of the canonical AI benchmarks, one of the first benchmarks that really leveraged big data in order to track what is going on in the world of AI. And you'll notice that we went from performance of AI systems that was 90% relative to human baseline to greater than 100% in 4 or 5 years. So this benchmark served the research community for a good 4 to 5 years before we kind of saturated it. Whereas now we're kind of in a territory where some of these new benchmarks like competition level mathematics, we have gone from a performance that was close to 10% all the way to 90% in less than a few years. So we're getting a lot better at a lot harder problems. And for reference, the human baseline level performance for competition level mathematics is the performance of a 3-time international math Olympiad gold medalist. So it's not like I was sitting around at home and trying to attempt these competition level mathematics problems. Again, we now really only have a couple of task categories where AI is not exceeding human performance. A second really big highlight from the AI index is that industry is really continuing to dominate frontier AI research. So if you look at where notable machine learning models are coming from by sector, you'll notice that up until 2014, the majority of these models came from academia. Since then, a massive gap has opened up to the point where in 2023, there were 51 significant systems that came from industry, compared to just 15 that came from academia. And if you look at the breakdown of foundation models, which are again these very powerful AI systems like GPT-4, Gemini, and Claude that can reason and think very flexibly, are trained on massive amounts of data, you see a very similar breakdown. The majority of these models come out of industry rather than academia. And since 2019, the kind of leading organizations in this domain have been Google, have been OpenAI, have been Meta, have been Microsoft. So it's not necessarily super surprising to see who kind of rises to the top there. Now, industry is doing a lot better in AI, and you kind of might be wondering, why is that the case? Are they just paying people at OpenAI and Anthropic more than academics? Maybe the kombucha and some of these new wave Silicon Valley offices just really good. I think the story here is really one of scale and the cost of scaling. So what you see on this particular chart is you see the estimated training cost of select AI models from 2017 to 2023. And you'll notice that the cost really kind of balloons from roughly $1,000 in 2017 to close to a couple of million in 2020, all the way to 100 million, if not more, in 2023. And we're kind of at this point where some of these leading models like GPT-4, we estimate cost $80 million to train, and Gemini Ultra close to 200 million as well. And the reason these models are becoming so much more expensive is really one of scaling. So I'd be curious to kind of know from the audience, maybe you guys can kind of raise your virtual hands, who here has heard of the concept of scaling laws when it comes to AI? So I see maybe a couple of hands that have shot up, but not too many. So scaling laws is this kind of concept that was discovered in around 2020 when the AI research community was creating GPT-2 and GPT-3. And it's this idea that if you take this transformer architecture, so the transformer is a model that was introduced in 2017 by a team of Google researchers. It was the kind of model that introduced this methodology of next token prediction. If you take this architecture and you just feed it increasing amounts of data, it tends to do a lot better on a variety of tasks. And this was kind of noted. And since then, a lot of these companies have just basically been making bets that if they feed these systems increasingly greater amounts of data, and increasing the amounts of data requires more computational resources, they will get a lot better. And that has been the case. But obviously, as you see on this chart very clearly, as you scale up the computational resources on the x-axis, you scale up cost on the y-axis. And that's really kind of what's going on here. We're kind of making a bet that AI is, you give it more data, it gets a lot better, but we're now at a stage where some of these kind of new wave AI systems are being trained on percents of all of the data that has ever existed on the internet, and they're being trained for several iterations at a time. Now, there's also an interesting geopolitical question that needs to be asked here, which is, who is leading as the kind of top source of AI models? So at the moment, we have the United States as kind of the place where a lot of these AI models are coming from. They do better than China, the EU, and the UK as one of the top sources of AI models. And it's not only the case that the United States is leading. The United States, I would say, has a pretty sizable lead when compared to countries that are in the vicinity like China or potentially France. A fifth highlight, and I think one that has a lot of very important implications in the world of responsible AI, some of the presentations that we saw earlier today, we're talking a little bit about model standardization, is just the observation that it really seems to be the case that there is a lack of robust and standardized evaluations for LLM responsibilities. So what do I mean by this? So what you're seeing on this particular chart is you're looking at a variety of notable AI models. We have GPT-4, we have Llama 2, we have Claude 2, we have Gemini, and we have Mistral. These are kind of flagship models that at the time of publication were arguably the best models that each of these developers had released. So we have OpenAI, we have Meta, we have Anthropic, Google, and Mistral. And you can see what particular general capabilities benchmarks these models are tested on. So they're tested on, for example, MMLU, which is a benchmark for general language understanding. Every single developer is testing on MMLU. All of them are tested on Codex Eval, which is a benchmark for coding and code completion. All of them also test on GSM-8K, which is a benchmark of mathematical understanding, most likely on the grade school level. But when you fast forward into the world of responsible AI, so this is looking at benchmarks that test how responsible these models are, you'll see there really is no consensus. Some of these developers are testing on truthful QA and real toxicity prompts, which are benchmarks respectively for how honest and truthful models are. And toxicity looks at how likely it is for a model to be toxic. Some of these developers are testing on BOLD and BBQ, which are benchmarks for bias understanding, but there really is no standard testing suite that all of these developers are using. Now, we didn't kind of speculate in the index as to why this is the case. On the one hand, you could imagine that these developers might be cherry picking particular benchmarks that make their models look the best. On the other hand, you could imagine that some of these developers genuinely believe that certain benchmarks are better than others. But in any case, we're kind of now in a world in which AI is being widely deployed. It's being widely used. And as such, we would want to put ourselves in a position to have some kind of standardized suite of evaluations that could really comprehensively look at what AI does and what AI can possibly do, and enable some kind of standardized model to model, benchmark to benchmark comparison, especially in the domain of responsible AI. Now moving into some more economic highlights. Generative AI investment has skyrocketed in the last year. We kind of went from having roughly 3 to 4 billion of this type of investment in 2022 all the way to 25 billion in 2023. And I think this is reflective of the fact that a lot of venture capitalists seem to be really well aware of the fact that this technology has a lot of productive potential, and they're betting really majorly on a lot of these companies that are developing and fine-tuning some of these models. From a productivity standpoint, and this is personally one of the highlights that I was the most excited to see, the data now really does seem to suggest that AI is associated with more productive and higher quality work. And you're seeing this now across various studies and with also a variety of interesting caveats. And I think this is exciting to see because, when AI started kind of emerging onto the scene, you saw a lot of economists getting giddy and getting excited about the potential that this technology had to predict and potentially improve what workers would be able to do. But obviously, until we know what the data says, predictions and, let's say, premonitions about what this technology could do are just that. Well, now the data does seem to give us some kind of answer. So this first slide is from a Copilot study that is comparing the cross-study task completion speed of a variety of Copilot users. So on this particular task, you basically had 5 different groups, and there were 5 different studies. And in each of these studies, there was one group that was not given access to an AI assistant like Copilot, and there was another group that was given access to this assistant. And each of these groups in each of these studies was doing the exact same task. And you'll notice that across studies, the Copilot users, the ones that were using AI, were able to get their work done anywhere from 73 to 26% less time than those that did not have access to Copilot. And you see similar results that come out of the world of consulting. In a study of consultants that were given GPT-4 versus those that weren't, those that used GPT-4 were more productive, did work of substantially higher quality, and were also doing work a lot quicker. Now, there's a couple of additional caveats that some of this data reveals. Now, I think the first one is that it seems to be the case that although workers across the board generally benefit from AI technologies, that is, both low and high skilled workers level up as a result of using AI, it seems that the impact of AI technologies is substantially greater for lower skilled workers than it is for high skilled workers. As in pre-AI, there is a fairly substantial gap between the capabilities of low versus high skilled workers. And then post-AI, the gap still remains, both level up, but lower skilled workers level up more than high skilled workers. So AI is potentially a tool that could really bridge the gap in the capabilities of what some of these different agents may be interested in doing. So that's kind of caveat number one. Caveat number two is that it is still very important in a lot of these studies to be keeping humans in the loop. There was one really good study where there were 3 groups, and each of these 3 groups was given the exact same task to do. Now, one of these groups did not have access to AI tools, and the other 2 groups did have access to AI tools. Now, of the 2 groups that had access to AI tools, they were both given the exact same AI, and the only difference was that one of the groups was told that the AI that they were given was a quote-unquote good AI, so an AI that got the job done reliably, and the other group was told that they were given a bad AI, so that is an AI that was sometimes good but prone to making mistakes. Now, when you compared the output of the 3 groups, the AI groups did better than those that didn't have AI. But of the 2 AI receiving groups, it was actually the group that had access to the quote unquote bad AI that did better than the group that had the good AI, even though they were the exact same AIs. And the researchers basically speculated that those in the study that had access to the quote unquote good AI, they were told that it was good and they just kind of went on autopilot mode. So I think there's an important conclusion in the study there that even when you use AI, it's important to keep humans in the loop and not necessarily forget about integrating those in the workflow as well. Scientific progress is also massively accelerating as a result of AI. You see this in so many different domains with materials discovery, medical discovery, and I think this is something that I'm particularly very excited by because very often in the news, you kind of hear all this talk about LLMs and large language models, but I think this is where some of the most exciting stuff is actually happening, What you see on this particular chart is the predictions of alpha-luminescence for luminescence classifications. So for those of you that are unfamiliar, luminescences are mutations to human protein structures that could be benign, they could be pathogenic, but the kind of important thing to know for the purposes of our discussion is that before alpha-luminescence, it was estimated that of the roughly 75 million different luminescence mutations, human annotators could successfully annotate close to 1%. So that, again, is 1% of the 75 million. Then alpha-luminescence comes along, and alpha-luminescence has thus far been able to classify 89% of all of these 75 million variants. And you see the prediction classifications on the slide here. So that kind of really illustrates to you the power of AI and what AI could do. A ninth highlight on the regulatory side is that there are simply way more AI regulations in the United States than ever before. The number of AI regulations in the US has jumped from around 1 in 2016 to 25 in 2023. And it's really the case that these regulations are coming from a diversity of agencies. So it's not just the case that the Census Bureau or one particular department is thinking about these. You have the executive office of the president that is getting in on the party. You have the Commerce Department, the Center for Medicare. So really, agencies across the United States are thinking about these tools. And it kind of goes to show you that probably in whatever line of work that you are in, there's going to be some kind of forthcoming regulatory guidance about how you ought to be using the tool. Last highlight before I open the talk up for questions. It's now the case that people across the globe are becoming more cognizant of AI's potential impact and also substantially more nervous. What you see on this particular slide is the percentage point change in opinions that people have about AI by country. So Ipsos did a survey in 2022 and also 2023 where they asked people the degree to which they agreed with various questions. And in this particular case, what I've highlighted is the response rate for people agreeing with the question, products and services using AI make you nervous. And you'll notice that for virtually every single country included in the sample, there was a substantial increase in the amount of nervousness reported in 2023 compared to 2022. And to me, this really illustrates that AI is here. It's on the minds of a lot of people. And now that it's on the minds of a lot of different individuals, policymakers and business leaders have a responsibility to get it right in terms of thinking about how they manage this technology and deal with this technology. So that concludes my presentation. I've put a QR code up for the index if you guys want to dive through the report, but would be more than happy to answer any audience questions that you guys might have at this time. Thank you.
Wonderful. This is very good. We have a question, and when you're talking about the trend and the future, among other things, everything from technical knowledge, software, hardware, all that development, and you have shown us the progress over time.
Yeah.
Can you speak a little bit about quantum computing and the events that could happen with AI? The cost of quantum computing and so forth.
Yeah, I would say a couple of things. So, I think a lot of the progress that we've seen now has been driven by the scaling concept that I kind of talked about in the presentation. Everybody's kind of using the same architecture and they're just pumping more data into it. I think there's open questions as to how far that's going to get us in the future, as in we're already training some of these models on percents of everything that's ever existed on the internet. So it's clear that these models aren't, as efficient as the human brain is. And it's kind of open question as to how much more data can we realistically give them. We just might be running out of data at some particular point. Also, I think there are limitations to what transformer-based models can do. It seems like they still struggle with hallucination. They still struggle with planning. And you have to kind of wonder if the transformer is going to be the last architecture on the horizon, or if perhaps there's going to be some new researcher that is going to think of a new way of developing and representing some of these models. So I think the models will definitely get better in the future. I think it's just a question of how much better they will get and what is going to be their potential to kind of impact some of the ways in which jobs are being done.
And talking about hallucination, there's a question on that, which is, do you think the GenAI hallucination cost more than the benefit? For instance, one would spend more effort to identify the hallucination that has no way going to be 100% eliminated.
No, I think AI has a lot of benefits. I just think you need to be careful when you use it. I think the lesson from this presentation is not to not use it at all. In fact, I think there's other data in the index that talks about how businesses that use AI are now putting themselves in a position to kind of get ahead of those that don't use AI. But I think the kind of key idea is that if you are not careful, if you're just kind of shutting off your guardrails, then you really potentially put yourself in a position to kind of use this technology in a bad way or to have some kind of bad outputs. So I think it's just about accepting that the technology is somewhat flawed and kind of coming to terms with that, but not throwing the baby out with the bathwater, so to speak.
Yeah. There's another question on, we all know the risk of misinformation, disinformation coming from AI. The question is more about how can we use to detect and mitigate the spread of misinformation and disinformation on social media platform.
Yeah, I think there's a lot of new models and a lot of new research being done on this particular element. So there's researchers that are thinking very critically about this. I also think we might need to kind of change our strategies for how we actually do some of this disinformation reporting, as in it might not necessarily be super feasible for there to be fact checkers that are verifying every single piece of media that is outputted. It might more so be the case that you would want somebody like Joe Biden or the White House to kind of include with their releases some kind of digital tag that kind of affirms and validates that this is actually coming from their office, rather than kind of having to rely on third parties that would do that. So I think there is more information that we can potentially get, but I do think that we need to kind of be strategic and mindful about how we actually engage and think about these kinds of disinformation efforts.
Thank you so much, Nestor. I mean, definitely, I can speak about myself. There's a lot of demystification that happened during your short conversation. And thank you again for spending your time.
No, it's a pleasure.